today we'll be dealing with the electric dipole approximation, which is the application of the interactions with classical radiation field. So in the previous case, we had considered the case of a monochromatic field of the plane wave. So just a recap of that. So any classical radiation field can be expressed as this Hamiltonian, that is H is equal to P square by 2m plus E phi of x minus E by m C into A dot P. And we saw that in a monochromatic field of plane wave, A can be represented as 2A0 epsilon cos omega by c n dot x minus omega t. And we saw that epsilon and n are the polarization and propagation directions. Again this A, then the cos term can be written in terms of the exponential term e raised to I omega by c n dot x minus omega t plus e raised to minus I omega by c n dot x minus omega t by 2. And we were taking about the absorption case, that is e raised to minus I omega t. We took the term e raised to minus I omega t. So what is it? The coefficient of e raised to minus I omega t is, you can see that it is here. Okay. Sorry, it is here. Okay. This is it. This one. So here you can see that we have a term e raised to I, the coefficient is e raised to I omega by c n dot x. So we are going to focus on this aspect e raised to I omega by c n dot x for the electric dipole approximation. So here what we do is, in this approximation, this omega by c, okay, we have omega by c is equal to 1 by lambda bar. And we assume that in electric dipole approximation, the wavelength of radiation field is far greater than the atomic dimensions. So here is where the approximation is, that is the wavelength of radiation field is very much greater than the atomic dimension. That is how we can tell about it. So we know that h cross omega, the energy term, is approximately equal to Z square divided by R atom. Okay. Or we can say that 1 by omega. From this, what is 1 by omega? It is equal to H cross atom, R atom, divided by Z square. Or in terms of, we have this expression omega by c is 1 by lambda. So we'll just put it in terms of that. Therefore, we have c by omega. Okay, just multiply with c everywhere on both sides. R atom divided by Z square. And we know that c by omega is nothing but lambda bar. It's approximately equal to, okay, CH cross E square. These are all constants. Okay, that is given by 137. You put the value of C H cross and the electric charge. R atom divided by Z. Or you can say that R atom is the atomic dimension. So R atom divided by Z lambda bar is approximately equal to Z by 137. Okay. If atomic number for lighter atoms, okay, for lighter atoms, this will be a very small number. It will be very much less than 1. Okay. That is how we tell that if the wavelength is far longer than the atomic dimensions, then we go in for an electric dipole approximation. Also we tell that it is for the lighter atom, because you can see that here atomic number Z is Z and Z divided by 137. So he said if it is a very small value, lighter values, then this will be very much less than 1. If that is a condition, okay, if that is a condition, then what happens to e raised to I omega by c? Here you have omega by c. What is omega by c? What is omega by c? It is 1 by lambda bar. So you can see that when lambda bar is very much greater, this value will be very small. E raised to I omega by c n dot x will be very small. That means you can expand it binomially. So I am just taking that value, e raised to I omega by c n dot x can now be expanded binomially as 1 plus I omega by c n dot x plus etc. So what we do here is omega by c is very small when compared to 1. You can see that. So what happens? We can restrict it by the first leading term. There is a 1. So now I can replace e raised to I omega c into n dot x by 1. And this is called the electric dipole approximation. Okay. So when you are asked to write about electric dipole approximation, these things you have to put in. That is the wavelength of the radiation field. Okay. The wavelength of the radiation field must be far greater than the atomic dimensions. And this formula you have to put in. So now when again going back to our monochromatic field of plane wave, there you can see that we had the term n e raised to I omega by c n dot x minus n dot x epsilon dot p I. Okay, so this is what we had seen. And now in this case what we do, e raised to I omega by c, this term can be replaced by 1. So this equation will look like n p I. Okay, so I can put this epsilon outside, is a propagation direction. Now look at this. So we'll just put this as equation 1. This as equation 2. So substituting 1 in 2, you will get this equation 3. Again now I am just going to consider the commutation relation x comma x0. What is it? You know, this can be written as x comma p square by 2m. So if you take 1 by 2m outside, what you have inside? X comma p square. This you have learned, the commutative relation between x and p square. It is nothing but IH cross 2p by 2m. So it is equal to IH cross p by m. So if it is x, you can say that it is px. Okay. So now we can write this, if it is px, okay, it is propagating in the x direction, or we can say that epsilon n, this p can be replaced by the commutation x comma h0, okay, I. So what all other factors should we have? So here it is only p, but here we have x h0. So m by IH cross, okay, that should be included. So I can write here instead of this m by IH cross. Okay. Also again you have, what is H0? Acting on I. Acting on N is equal to the energy eigenkette. Okay. So now we can expand this commutation relation here. Let's put it as equation number 4. Okay. Now expanding this, we have MIH cross, okay, N XH0 minus H0X I. So you know, we have H0 acting on this cation, okay, and this H0 acts on Brian. So how will this look like? It is equal to M by I cross, okay, minus, so H0 acting on N will be give you En N. So I have En is minus En, so I can write minus of En minus Ei, okay. Then you have that x inside factor, N X I. Okay. Now this I can be absorbed here. So we have, in terms of omega, you can write H cross omega Ni. So I put this I on top, minus 1 by I means it is I. So it is I M omega Ni N Xi. So this is my equation 5. So now we have seen that we have got e raised to I omega by c n dot x epsilon dot p in terms of expectation n and I as is equal to I m omega Ni n Xi. Now again going back to the monochromatic field of the plane wave, we have sigma ABS as equal to 4 pi square H cross by m square omega E square H cross C, which we have put as alpha, modulus n e raised to I omega by c n dot x epsilon dot p I the whole square delta En minus Ei minus h cross omega. Okay, this is what we had. Now this we have formulated. This we'll put it as alpha because it won't be a, crowded thing. So this we can put it as 4 pi square h cross by m square omega alpha, and this is modulus square. So here I is there, modulus square is 1, m square omega ni square. So I have to write all those things, m square omega ni square. Then you have that modulus n xi the whole square. So if you write delta En minus Ei minus h cross omega in terms of omega, you have delta omega ni minus omega, okay, by h cross. So you can see that a couple of terms cancels. This h cross and h cross gets cancelled. M square and m square gets cancelled. 1 omega and here 1 omega gets cancelled. Okay, so you are left with 4 pi square alpha omega ni modulus n xi the whole square delta omega ni minus omega. Okay, now we'll define an oscillator strength. Okay, oscillator strength classical electrodynamics Fni. Okay, it is defined as 2m omega ni by h cross modulus of nxi the whole square. So this we'll put again equation numbers. So let this sigma abs be 6 and our oscillator strength at 7. Again, Thomas-Ritchie-Kuhn rule, sum rule says that sigma ni is Fni is equal to 1. Okay, let's put that as 8. Now looking to the equation 6 sigma abs, you can identify 2m omega ni h cross modulus of n xi the whole square. So here you have modulus of n xi the whole square. Then you have an omega ni here. Now what I have to do is I just have to multiply m, okay, on top and bottom, and also an h cross. So how will this equation look like? Okay, I'll just integrate this equation 6. Okay, so how will it look like? Integral sigma abs with respect to d omega is equal to, I can replace integral here right side by summation also, 4 pi square alpha omega ni modulus n xi the whole square delta, of course, delta omega ni minus omega. Again my alpha is nothing but e square by h cross c, no? Alpha is equal to e square by h cross c. So I can just substitute here in this equation 9 is equal to sigma 4 pi square e square by h cross c omega ni modulus n xi the whole square delta omega ni minus omega. So now I'm going to take this one. Okay, 4 pi square. So I mean 2m omega ni by h cross. Okay, 2m omega. So I have 4 here. So I can take a 2 ni. Then you have that m. So I have to multiply m on top and bottom by h cross is there. So now I can write this as sigma 2 pi square e square, h cross is there, by c. This m also have to write down, m into c. Then I have that Fni delta omega ni minus omega. So sigma Fni is nothing but 1. So I can write this equation again as 2 pi square e square by mc into mc. So you can say that here delta omega ni, you know, what is delta omega ni? If it's a Dirac delta function and it is equal to 1 only if they are equal. Okay. So I can very well write this equation as 2 pi square e square by m into c. Okay. So that is my integral sigma a ds d omega. So here you can see that in this equation the h cross has disappeared, and this is just the oscillation sum rule, which is already known in classical electrodynamics. Historically speaking, this one is the first example of how new quantum mechanics led to the correct classical result. This sum rule is quite remarkable because we do not specify in detail the form of the Hamiltonian. So this is a quite important result, this electric dipole approximation, which has led to the classical result. So all of you do learn this. It's quite important, electric dipole approximation. So it is historically also it is important because we cannot separate any formulations like classical, quantum and all. But then when approximations comes up, you can reduce the quantum approximation to classical approximation. So this is one of the examples. Thank you all.